So this video is going to dive into some of the characteristics of functions. When we talk about functions, we talk about something that's a relation that passes a vertical line test. We don't have those repeats in the domain. So let's talk first about domain and function. The book definition, formal definition of domain is the set of all defined values or inputs of the independent variable. Think of this as your x's, the things that you want to plug in and see what comes out of it. Then we have the range. That's the set of all defined values or outputs of the dependent variable. Think of this as your y values. So if you think of an xy chart or f of x chart, your domain is your x's and your range is your f of x or your y's. The two things that we're going to dive into first are relative minimums and relative maximums, or more generally, maximums and minimums. A relative minimum is defined as f of a for some function f when there is an interval, x1, x2, that contains a so that all the x's between there has a smaller than or equal to f of x. Relative maximum looks a lot like that, same kind of definition, except f of a is bigger than or equal to all the f of x's in that interval. So let's put this into some practical use. I've got a couple of functions up here. This first function has 3 points. Sometimes I refer to them as the peaks and the valleys of that function. And we're looking at those. And if you look, we'll take this first one. I'm not talking overall, but I'm talking right around to this point. If I just kind of look in this point's neighborhood and look at everybody around him, he is the lowest y value that's here. He is sitting in a valley. So we would refer to this as a minimum. Now, it is not the overall minimum because there's another valley over here. This is also a minimum, but it is a different kind of minimum. This first one is called a relative minimum because relative to everybody else around, that is the smallest value. This one over here, this is where this whole function bottoms out. If I'm looking at y values, this is the lowest point we ever get to. So we refer to this as an absolute minimum. Some books just refer to it as the minimum, and this as the relative minimum, but I think it's easier to put the title absolute on here, so this is the absolute minimum, this is just a relative minimum. This point up here, again, if we look at just what's going on in his neighborhood, relative to all the people around him, this is a peak, or a maximum. You'll notice that this function continues on forever and ever up on both ends, so we're never going to get to an absolute maximum, but for our purposes, this is a relative maximum. It is the highest point in this area. This is the lowest point in this area. This is the lowest point in this area. This one just happens to be also the lowest point in the whole graph. Sometimes you will have an absolute, sometimes you will only have relatives. So if you look at my second example here, I only have relatives in this one. I don't have an absolute maximum because this function continues on. I don't have a relative minimum because it also continues on in the negative direction. So if we're thinking of this continuum of y values or ranges, it never gets to a bottom range or a top range. It continues on and on in both directions. So these 2 points are maximums, and this one is a minimum, but it is not an absolute. It is what we call a relative maximum. This is a relative minimum. So relative to the people around, the other points around them, and that's what this definition is saying. Relative to the other points around, a minimum is the lowest point. Relative to the other people around, a maximum is the highest point, the biggest point. Now, there's another way that we can look at these graphs besides just looking for those peaks and valleys. We still want to look for them, but we also look for things about what the function is doing. And there's 3 things that a function can be doing. It can be increasing, it can be decreasing, or it can be constant. Let's start with increasing. Here's the formal definition. This is basically saying as the x's get bigger, the y's are going to get bigger. That's what it means to be increasing. So if I go back to one of these functions, I'll just take this last piece. As we continue to the right on the x-axis, the y's are going up. This thing is traveling upwards or increasing. Now if I pick between these 2 points, as I continue on the x-axis, as I move from left to right, my y values are coming down. So this would be an example of decreasing on a function. If I go between these two, it's not as extreme, but this is still increasing. And over here, this is still decreasing. So sometimes we define them based off of the x's. Sometimes we just write them on a graph. So if I had some x values in here, if I said x is equal to 2, and out here, x is equal to 5, then I would say from the left side until I get x equals 2, this is decreasing. So using mathematical symbols, I would say something like this. From the left, so negative infinity, until I get to 2, I am decreasing. This function is going down. At 2, something changes. I have this relative minimum. So from 2 to some other point, this thing starts increasing, and that point happens to be 5. So now I'm increasing. I'm going up. My y values are increasing as x goes left to right. Now when I get to 5, I have another maximum. I have another one of these turning points. So at 5, things change again. And since they aren't going to change again, we're going to put an infinity symbol, and we're going to say from 5 all the way to the right-hand side, this thing is going to decrease once again. So sometimes you'll see people mark it on the graph, going up, going down, going up, going down. Sometimes you will see people listed out as from negative infinity, so from the left until 2, I am decreasing. Between 2 and 5, I'm increasing, and between 5 and infinity, I'm decreasing again. And you'll notice we're using x values. We're using this x-axis to tell me where those changing points are at. The decreasing, obviously we're looking for things that are bigger. The constant I didn't talk about because there weren't any here. So let's look at an example where we have constant. This is where the y values are the same. So if I had a graph like this one here, we can pick out those increasings. Here's 2 increasings. Here's a decreasing, where the function is going down. But notice what's happening in here. X continues to change, but y doesn't go up and y doesn't go down. So y stays the same, so these are a constant. Here's another one up here. The y values stay constant. So when we talk about functions, we can talk about their maximums or minimums and determine if they're relative or if they're absolute. We can talk about functions increasing, decreasing, or being constant. The last thing we need to talk about with functions is the transformations of functions, how these functions can change, how they can move. So we're going to start with a generic parent function, f of x. This can be any function. It could be an absolute value, it could be a power, it could be a quadratic, it could be any function. This works for any function. But we're going to make some changes to it and call it g of x. So notice f of x is sitting right in here. Here is the parent function, but we have done a whole lot of things to it, and we need to figure out what those things do. So I'm going to start with the shifts. There are 2 shifts we talk about. There's a vertical shift and a horizontal shift. A vertical shift is an up and down. So if we have a plus number on the outside, it moves it up. If we have a minus number, it moves it down. Plus 7 moves it up 7. Minus 2 moves it down 2. That's the outside number. Now, if we have a number on the inside of the parentheses, now we're looking at what's called a horizontal shift. Now, we have to remember that parentheses can be an absolute value. It could be a fraction bar. They work like parentheses, or it can be actual parentheses. So this particular parenthesis is going to tell me the horizontal shift. Now, here's what's confusing about it. It's in parentheses, it's actually backwards. So if I have a negative number, it's going to move it to the right. If I have a positive number, it's going to move it to the left. It's backwards of what you would think, like the vertical shift. Positive for vertical moved up, negative moved down. Inside the parenthesis, it's backwards. Positives move left, negatives move it to the right. There's two more transformations that we do. These just move it around. There's two out front that do some other things. Let's start with the sign in front. Normally we have a positive sign out front. But if we put a negative sign out front, we do a reflection over the x-axis. We mirror this. If a function was pointing up, now it's pointing down. If it was pointing down, now it's pointing up. So we reflect it over the x-axis. That's the sign that's out in front. When we talk about the value out front, this does something a little different. This does what's called a vertical stretch or vertical compress. So we need to look at the value of a. We just look at the a. We don't care about the sign in front. So I'm going to put an absolute value in front of this because we don't care about the sign, just the actual number. So if that number that's sitting in front of the original function is bigger than 1, it is a stretch. Think of when you grab a hold of a picture and pull on it, it gets longer. People in the picture get taller. Things get stretched out. That's when you see a number bigger than 1. If you have a number smaller than 1 but still above 0, think of your fractions. Think of a half. Think of 0.25. Things that are between 0 and 1. Now we have what's called a vertical compression. This thing has been squished. And when you squish a photo, people in the photo tend to get bigger. They get compressed and they have to fall out a little bit. So that's what's called a vertical compression. That's the number that's in front. So just to show you an example of a typical function we may see. Here is a quadratic function. This is the parent. Nothing has changed with this. We know what it looks like. We can put this into our graph. So now I'm going to make some changes to that. The parent function is still sitting here, x squared. It's right here. But they have done a few things to it. Out on the outside, they have moved this up 4 places. It has been vertically shifted up 4. In this parenthesis, they have done a horizontal shift. They have actually moved it left 3. Remember, things in parentheses are backwards. The sign in front is telling me this has been reflected. So instead of this quadratic pointing up, it is now pointing down. That negative tells me my quadratic has been reflected. And the number here is definitely smaller than 1, so we're looking at a compression. A vertical compression. So this thing has been squished. So if it's a nice U-shaped, it might be a fatter U now. Again, these things work with any function, any type of function, any parent, absolute values, quadratics, cubics, lines, they all work. These things affect them all the same. So that's the last thing we're going to talk about as far as transforming our function.